In this second tutorial, we will be able to graph logarithmic functions and be able to state the domain and the range. So let's flip over to this page of our notes, and if you have not already guessed from our review inverse tutorial, exponential functions and logarithmic functions are inverses of one another. So what I'd like to do is graph this exponential function y equals 2 to the x, we did that in a previous tutorial, and then I'd like to graph this logarithmic function y equals the log base 2 of x, and we'll see how these relate. So let's first start. I'm going to color code it again. Here's my red one. Y equals 2 to the x. Let's remember how to do that. H is 0, k is 0, a is 1. So this is just a normal exponential with a base of 2. The 0 power always makes me go up to the 1. The first power, at least when my base is 2, would make my output be a 2. My second power would be my base squared, so 2 squared is 4. My third power would be 2 cubed, which is 8. 5, 6, 7, 8. And over here we've got the 1/2 and the 1/4 and the 1/8. And we remember that there's a horizontal asymptote for this exponential function. So we've graphed these already. And I'd like to look at that graph. Here we go. Okay, so now when we want to graph its inverse, and I'll prove to you in a bit why this is the inverse, when we want to graph the inverse, much like when we wanted to graph the inverse of a parabola, something like y equals the square root of x, we didn't want to just plug anything we wanted for x. Yes, of course, we could plug in a 17 into here, but I don't frankly know what the square root of 17 is. I'd rather plug in intelligent values as my inputs, things like 1 and 4 and 16 and 100, perfect squares, because those would be nice outputs. Here, I want to make sure that x is a nice input. I know that I can basically plug in anything, actually anything that's positive, but I don't want to just plug in anything. I want to plug in the special values that deal with my base of 2. So if I'm talking about the log base 2, I'd love to see a 1 right here. If I'm talking about the log base 2, I'd love to see a 2 right here. If I'm talking about the log base 2, I'd love to see a 4. And log base 2 of 8. These are all nice values because they start to represent the powers of 2. Here's 2 to the 2 to the 0 power. Here's 2 to the first power. Here's 2 squared. Here's 2 cubed. So each one of these logarithms, again, logarithms represent exponents. Each one of these exponents is one of my special powers of 2. 2 cubed is 8, 2 squared is 4, 2 to the first is 2, and 2 to the 0. What about my fractions? I'd love to see something like 1/2 for x, or I'd love to see something like 1/4 for x, because these are also going to be nice exponents. 2 would have to be raised to a negative 2 power to make my fraction of 1/4. 2 would have to be raised to a negative 1 power to become my 1/2. So these are all nice inputs, and with logarithms it's a little bit trickier to graph, so we want to make sure that our inputs are nice values. Okay, so now let's graph each one of these ordered pairs that we just found. Remember, these are all equal to y. Those are my outputs. My exponents are my outputs this time, as opposed to over here where my exponents were my inputs. Now my exponents are my outputs. So that's why my inputs are going to be 1, 2, 4, 8, 1/2, and 1/4. These are some nice input values. So my input is a 1. That means from my 0, 0, I'm going to go over 1. And I'm doing, by the way, I'm doing it in a different color. I would suggest that you do that as well. I'm doing mine in blue. When I go over 1, that is my 0 exponent, because 2 to the 0 power is 1. So 1, 0 is where I would stop. The next input that I want, because it's base 2, is to go over 2 units. And when I go over 2 units, 2 would be raised to the first power to get a 2. So 2 units to the right, and I get to go up 1. Next good input is 4. We're skipping over the 3. 2 squared becomes 4. So when I go over 4 units, 1, 2, 3, 4, I get to go up 2. Remember, my outputs are my exponents, and this is the squared exponent. The next good input is 8, and that happens when 2 is being cubed. So I have to go over 8 units, 1, 2, 3, 4, 5, 6, 7, 8, before I can go up to the cube, before I can go up to the 3 as my output. And that's going to be enough that fits into my graph right now. But I do have some values over here that I'd like to do. These represent those cheat points, or at least the inverse of the cheat points. When I go to 1/2, that happens when my exponent is negative. 2 to the negative 1 is 1/2. So when I do an input of 1/2, I get to go down to the negative 1. And when I do an input of 1/4, that was the exponent of negative 2. So I have to go over 1/4 so that I could go down negative 2. And hopefully you realize that in this blue graph that we actually have a vertical asymptote. Now don't be confused that I'm graphing two different functions on the same axes. That's why I'm color coding. But this is what a logarithmic function will look like. And now that I've graphed both of them on the same set of axes, you can see that these indeed are inverses of each other. You can imagine the line y equals x going right diagonally through this graph patch, and they are exactly symmetrical. In fact, you can look at any of the ordered pairs and realize that they have just swapped the x's and the y's. I'm looking at this ordered pair right here on the red. That was 2, 4. On the blue, I have an ordered pair 4, 2. So what you need to understand when we're graphing logarithms is that we are indeed graphing the inverse of an exponential. So since exponentials basically look like this type of graph, the inverse is going to look like this type of graph, and that's important. But it's also important to understand that we get to pick whatever we want for our inputs, and we should make our inputs nice values, and that depends on what our base is. These values of 1, 2, 4, and 8 are going to change when we deal with a base of 3. And I'm going to show you a couple examples to do that. I said that I was going to prove that these were inverses, so let's do that. So you understand that the log base 2 of x is equal to y. That's the logarithmic function that we just graphed. If I wanted to prove that this is an inverse with our exponential, first of all, I don't really like this form that it's in. So one thing that we learned in a previous tutorial is we can convert it out of logarithmic form and into exponential. Remember, we find the base, which is 2, raise that to the exponent, which is what is on the other side of the equal sign. So this is 2 to the y, and that equals the number, which is x. So these two Brown equations are identical, just in different forms. Now remember what we do when we're trying to find an inverse algebraically. We swap the x and the y. And if we swap the x and the y from this version, we get 2 to the x is equal to y. And lo and behold, that's exactly what we graphed over here, y equals 2 to the x. So these are indeed inverse functions. So that's a nice little proof there. One last thing, what do you notice about the asymptotes? Well, for the exponential, that's the red one, so I'm using my red, I'm using my red marker, exponential. The exponential has a horizontal asymptote. The exponential functions that we've been graphing have horizontal asymptotes, and the logarithmic ones that we're going to be graphing today, because they're inverses, if I could spell here, the logarithmic have vertical asymptotes. So when we find our starting point today, we're going to put a vertical asymptote right through that. Okay, so let's look at two examples. Oh, we've got our general form to talk about as well. General form has the a, the h, and the k, and you would see that they're in the same exact locations. A is always going to be that coefficient multiplied. In this case, it's multiplied to the logarithmic symbol. H is always hiding in here with the x. This time it's going to be hiding in parentheses. And k is always the number that's out here. They do the same exact thing. A affects the output. So if we have a value of A, whatever our output would be, we multiply by A. H shifts left and right, and K shifts up and down. And again, that's exactly what A, H, and K do in all of our graphing by transformation equations. Okay, so let's look at our example 1. We have y is equal to the log base 3 of x plus 2 plus 1. So let's first find our information here. A is going to be the value of 1, since there's nothing multiplied to this logarithm other than a 1. I'll put 1 times that stuff. So A is 1, so that's nice. Our outputs are just going to be our normal outputs. H comes in here, and that must be negative 2. Remember, we always take the opposite of that idea. Basically, what makes this equal to 0. And K is always just the number that we see out here. In this case, it's just plus 1, so it's plus 1. Positive 1. That means that HK will shift us 2 units to the left and 1 unit down. So what I'm going to do is I'm going to go on my graph patch and go to negative 2, 1 unit up, positive 1. 2 units to the left and 1 unit up. And I'm going to put a little star like I do before. Some people put a box, or some people put a heart. That's fine. Some sort of starting point. And because I know that this is a logarithm, I know that a vertical asymptote is going to go right through that star. And therefore, especially since it's vertical, we will never touch that asymptote. So the great part of doing graphing by transformations is putting this star here has done most of the equation. We've dealt with most of the equation already. We're finished looking at this part, and we're finished looking at this part. The only other important part is that the base is 3. And since the base is 3, we're talking about the powers of 3. Those are going to be my important inputs. And those are 1, 3, 9, 1/3, and 1/9. Those are the special values that I want to make as my inputs. I don't need to look at the equation anymore. All I need to do is understand how to graph these. These are my inputs, and my outputs will be the exponent that 3 would have to be raised to get each of these numbers. So from my star, this first input 1 means that I go 1 unit to the right, and that is the 0 power. So I stop and put a dot. My next input is a 3. Because it's base 3, I go back to the star. I always start at the star. So from the star, I'm going to go 1, 2, 3. And 3 must have been the first power, so that's why I get to go up 1. My next is going to be 9. So from the star, I'm going to count 9 units over. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is my smart input because that happens when 3 is squared. That's why I get to go up 2. I'm not going to count 27 units over from the star, but if I could, that's when I would go up to the 3, because that's what 3 cubed is, 27. I do need my 1/3 and my 1/9. Whether you know that these are the numbers or not, that's where they are. 1/3 from the star gives me my -1 exponent, and 1/9 from the star gives me my my -2 exponent. These are basically those cheat points. As long as they're there, I'm not going to whip out a ruler and measure to make sure that you're exactly 1/3 of a tick mark. Can't possibly do that. And there's our second logarithmic curve. This type of curve increases very fast at first, and then, though it's increasing the rest of the way, it sort of slows down. But it is still increasing forever. Let's talk about the pieces of information. We do have an asymptote in this case, and it is a vertical asymptote, and that is the equation x equals -2. And I'm sure you're going to make the connection that this equation of the vertical asymptote will always involve the value of h from over here, -2. The domain is something that's different because the domain does not even touch this vertical asymptote, and it definitely doesn't get on this side of it either. So the domain starts at this value, though we don't get to include it, -2. And then it goes all the way to infinity. So I'm going to do an interval notation from -2 to infinity. The range is what's pretty easy on these guys because the range points all the way down here, so negative infinity, and then it points all the way up here, so positive infinity. So you can do the set of all reals. Some people will do negative infinity to positive infinity. Let's look at our final example, example 2. This time we're trying to graph this logarithmic function, but this is a different symbol, the ln. Remember that this is going to be base e. There's a little e that's hiding there. You don't really see it, but you know that it's there, and this is base e. So we'll talk about that when we need to. Let's do a, h, and k. This is still a value of 1 for a, so our outputs are not being changed from what they normally would be. H in this time is 2. 2 minus 2 would be 0, so 2 for h, and k is a negative 3. So this time our star, our starting point, is going to be 2 units to the right and 3 units down. I'm going to go graph that first. 2 units to the right and 3 units down. There's my star. And I also know that that's where my vertical asymptote is going to be. So let's graph that right through that star. Can't touch that. So again, once we've graphed our star, we've dealt with, I would say, 2/3 of our equation. We've dealt with this quantity and we've dealt with this number. The only thing left is to deal with the value of our base, and our base is e. So now let's look at the good powers of e. Well, the good power for any base is going to be 1, because the 0 power is always going to be equal to 1. Our next numbers would be e and e squared, and then 1 over e and 1 over e squared. Okay, so we don't necessarily have any of these numbers memorized, well, other than the 1. E is approximately 2.7, so I'll put in the 2.7. And if you want to check on the calculator, or I'll just tell you, e squared is approximately 7.4. So these are going to be all approximations. I have no idea what 1 over e is and what 1 over e squared is. I could use the calculator for that, but again, these are really just the cheat points, and you'll see what we do when we get there. Okay, I have my starting point. I know that I'm always going to be going 1 unit to the right of that starting point because that represents the 0 power. So that's kind of nice. The next input, the next intelligent input is E, which is approximately 2.7. So from my starting point, I'm going to count over 2.7 so that I can go to the first power of E, because E to the first is 2.7. My next one is e squared, which is approximately 7.4. So now from the star, I'm going to count over 7.4. 1, 2, 3, 4, 5, 6, 7. And then 0.4 would be just a little bit off. And 7.4 happens when e is being squared. So I get to go up to the 2. I'm not going to go over 21 or whatever it is, whatever e cubed would be, because that's way off the graph patch. And again, please just make sure you put some points in here so that it helps you with your graph. 1 over e, whatever that number is, and 1 over e squared. Heck, 1 over e cubed you could do as well. Doesn't really matter what those numbers are because I'm not going to be measuring your points. And there's our third logarithm. This one is a natural logarithm, but we can graph that just like any other base. And let's do our final questions here. Our asymptote, again, we have another vertical asymptote. So it's an x equals equation. In this case, it's x equals 2. And again, that happens because h is equal to 2. We shifted 2 units to the right. Our domain depends on where we're actually starting, and we're starting this time at 2. We don't get to include the 2, so there's my parenthesis, 2 to infinity. And the range, like all the ranges of logarithmic functions, will be the set of all reals. Thanks for watching this tutorial, and I'll see you in class and we'll graph more logarithms. Oh, thank you. You're too kind. Bye-bye.